happy to have Tat telling us about current deformation.
Yeah, thank you. Yeah. So first of all, I'd like to thank the organizer for the opportunity to speak and for putting together this wonderful workshop. So I'll have to leave for another conference in the last 2 days, so I'll only be around today and tomorrow. But I still look forward to many interesting discussions and conversations. Okay, so the talk today is about global aspects of exactly marginal concurrent deformations. And you're going to see what I mean by global aspects soon. And from the title of the talk, it might sound a bit remote to the study of quantum gravity, but I hope that at least for those people who are thinking about distant conjectures, and also people thinking about generally symmetries, how symmetries on worldsheets might resonate with this talk. Okay, so the talk will mostly be about quantum field theories. So the talk will be based on work in progress I'm doing myself, and also I'd like to bring out 2 nice references. So there's a nice lecture notes written by Riccardo Borsato, where I learned basically everything about concurrent deformations. And then there's a nice paper by Sergei Dubovsky, Stefan Nigro, and Massimo Prati, which I draw quite a bit of inspirations from. Okay, so with that, let me just set the stage. So the talk today will be about the study of a family of conformal field theories that are continuously connected by exactly marginal deformations. So these theories, they naturally form, this space of theories naturally form what's called conformal manifolds, okay? And so the deformation that I'm talking about is basically just adding to a Lagrangian an exactly marginal operator, which has dimension equals to a space-time dimensions, and then I just let it flow, okay? So given that this is a manifold, then there's a natural way to assign a metric on this. And this is what's called a topological metric, which is defined by 2-point functions of marginal operators. And so with this notion of metric, then we can also define the notion of distance on conformal manifolds. And this will be connected to distant conjectures, at least the CFT distant conjectures. So what are we interested in studying conformal manifold in general? So one reason is that they are connected to massless fields in string theory and quantum gravity, which are the most important fields in effective actions in the target space. So for example, in string theory, worldsheet CFT corresponds to some classical solution of Einstein equations, and the marginal operators on the worldsheet correspond to some massless field in the target space. And the topological metric now naturally enters into kinetic terms of this massless field, okay? And in holography, similarly, a marginal operator will correspond to some massless fields in the ADS bulk. So this connects exactly marginal operators with some massless field in the target space. And on the other hand, there's also another reason why it's interesting to study conformal manifold, and this is related to the recent progress in the swampland programs, which motivates a series of distant conjectures, which are related to what's called CFT distant conjectures through holography. So this CFT distant conjecture basically concerns about the infinite distant points on conformal manifolds, and then to discuss some universal behaviors there, okay? And it has been formulated by these authors, including someone sitting in the audience. But I'm going to just state the 2-dimensional versions of the CFT distant conjectures because I'm going to focus on just 2 dimensions in the rest of the talk. So in 2 dimensions, the CFT distant conjecture basically saying that a 2-dimensional CFT, which are at the infinite distant point of the conformal manifolds, are related to some primary operators whose scaling dimensions vanishes in the limits. Okay, and this statement has been proven in this directions by the nice paper by Hiroshi and Ifan last year, but the other direction still remain as the conjectures. And I'm going to use this result later in the talk. Okay, so what I'm going to do in the rest of the talk is that I'm going to just discuss a large class of conformal manifolds, but a specific class of conformal manifolds in 2 dimensions, which are generated by what's called the concurrent deformations. Okay, and a key slogan of this today's talk is that this is an example where by understanding just the symmetry of the theory, we can understand the deformation class of this theory. So understand at least almost everything about the conformal manifolds where this theory is lacking, at least a subset of conformal manifolds where this theory is lacking. Okay, so this connects the notion of symmetries with the deformation class of conformal field theories. And so more precisely, the plan is I'm going to first discuss concurrent deformations in general. And then I'm going to discuss several concrete results. So first, we're going to show that there's actually very detailed structures on this conformal manifold. In particular, a rationally dense set of points on this conformal manifold are related to seed theories by just doing a discrete gauging. Okay, so and discrete gauging doesn't change central charge, so this is consistent with the fact that they form conformal manifold. And also, I'm going to show that using this perspective, we can connect topology with the 12 anomalies of the currents that is involved to build the current deformations. Lastly, I'm going to comment on enhanced symmetries on these conformal manifolds. What are their consequences after deformation? And also, I will provide the symmetry TFT perspective of this concurrent deformations. I'll say a bit more about what is sim TFT for people who haven't seen that before. Okay, so this is a plan of today's talk. Okay, let's get started. Let's just talk about what is current deformations. So first of all, I'm working in two dimensions. I'm going to always work in 2D CFTs. So in 2D CFT, a conserved current will have a conformal dimension 1. So that means that we can take a product of two currents. Then this will make up to a dimension 2 operators, and this should be a marginal operator. But the way I'm going to build a current is through these specific ways. I'm going to contract them using epsilon tensors. Okay. So this is how I'm going to build the current. And I'll refer to this operator as the current operators. So a zero-order question I want to ask is that given two currents, is it always true that the current operator remains marginal after a finite deformation? Namely, I'm asking whether it's exactly marginal or not. It's marginal at the starting point, but it might lose its marginalities after the deformations. And it turns out a sufficient condition that this operator remains marginal is that J1 and J2 generates two commuting U1 symmetries.
So, question. Yes. So if the theory is compact, so there's this discrete spectrum and unitary, then the current really is separate holomorphic and anti-holomorphic.
That's right.
Are you going to use that, or you're doing that?
I'm not going to use that. Yeah, I'm going to comment on that. So in that case, this reduces to JJ bar deformations. But then current deformation is more general. I'm going to give an example. Yeah, that's a very good question. So let me just give a counter example where this doesn't work. Go ahead.
When you say U1, do you really mean a compact symmetry or just an R symmetry?
Yeah, so in fact, it can be R symmetry also, okay. Yeah. Okay. But I'm going to say it's a U1. It's going to give me some more mileage. Yeah, but you're right. Just a abelian will work. Okay, so let me just give a quick counter examples. So suppose we have two U1 that are embedded in SU2. Then the one is generated by sigma x, the other is generated by sigma z. Then these two U1 don't commute. And then if we use that current to build an operator, that is not exactly marginal. Okay, good. And I'm going to present a proof of this. And let me just relate to the questions that Leonardo asked. So people have proven that if the current enhances into a current algebra, namely it becomes a current, then the JJ bar operator you built is exactly marginal. So that was proven by this. But then people didn't prove what happens if we don't assume a current algebra. So I'm going to present a proof where.
But what is correct? If the theory is compact and unitary, then current algebra is automatic.
That's right. That's right. So the example I'm going to give is a non-compact theories. Yeah.
Can you say? Should I think of? What I can't tell is this going to be a primary operator or it's not?
Yeah, I'm coming to that. Yeah, I don't need to assume it's a primary. In fact, there's a counter example. Yeah, let me come to that. So let's talk about examples, okay? And then this would clarify. So a simple examples which reduces to JJ bar is basically just an CFT of compact bosons. Okay. So in this case, the theories are parameterized by two parameters. One is the metric of the target space, and the other is the B field in the target space. And then all these two parameters can be generated by current deformation using currents like this. Okay. So this is familiar examples, and they are using, and this is the compact CFTs, and the U1 symmetry enhanced to Carroll currents. But let me give you counter examples. This is a non-compact CFTs. So the non-compact CFT is very simple. It's given by R4 sigma models. So the target space is R4. And on R4 sigma models, there are, of course, U1 symmetries that rotates the R2 of subset, okay? And so the currents, this is not shift symmetry, it's the one that rotates it. So this is the current. And it turns out that this current, first of all, is not a conformal primary, okay? And second, this current doesn't factorize into current and anti-current part, so you don't get the enhancements to current algebras. But still, you can use it to do current deformations. So if you use it to do current deformations, you generate this very complicated mass. Don't need to worry about details of this. But the point is that first of all, this is a nonlinear sigma models. But surprisingly, this is actually conformal invariant. Okay, and the fact this is conformal invariance will come very clear later. And it turns out that these things, if you translate it into the language of metric and B field, you can think of it as what's called a TST transformations of the flat space solutions. So TST transformation was first proposed by Looney and Martesina, and the way they think about this is that they just want to find the solution generating techniques. So this is just a solution generating techniques for Einstein equations, but we know that every solution of Einstein equation corresponds to some CFT. So that's why TST transformations can be thought of as some also CFT generating technique. Okay.
So it's not a primary, but is it a descendant?
It's not descendant either.
It's
yeah.
not anything, right?
Yeah, it's nothing. Yeah,
It's not a good operator. Because you're 1 plus 1, so there'll be logarithms.
That's right. Yeah, it's not. Yeah, there will be logarithms in a 2-point function. Yeah, but still it's a current. Yeah, and then you can still use it to build current deformation.
It's a bit like phi itself, right? Is phi a valid operator?
Yeah, the J is good, right? J is
No,
good.
that J I think is d phi is fine, but phi d phi minus phi. I think that one is bad.
So if you compute a 2-point function of J, then you will find logarithms. Yeah, that's right. Okay. So of course there are more examples that are given by just deforming by WZW models, and it has been discussed also in holographic context. Okay. Good.
It's not as well behaved as the.
Which means its correlation functions are not defined without further information. I mean, it's the same as you would say for phi in the non-compact scalar.
Yeah, I totally agree with that.
Scale that goes in the log.
That's right. Yeah, that's right. But it still won't stop you from doing concurrent deformation with this. So.
Well, for example, with phi, right, the 2-point function becomes negative.
Oh yeah, I agree with you.
Very bad, right?
Yeah, I agree with you. The 2-point function it looks terrible. There are some logarithms in that. But my point is that still, even though it's not a good current, but we can still use it to build a good concurrent deformations. Yeah. Okay, so these are the examples. So let me now talk about concurrent deformations in general.
And that's what he will care about.
In general, okay. So in the example I gave you, like in those cases, there are actually a classical Lagrangian. So one can actually do the deformations by solving a flow equation like this, because we know the currents, then we can do this. But more abstractly, we don't know the information about the currents in general, and how do we define concurrent deformation in abstract level. So the way to do that is that we first need to keep track of how the currents varies respect to a flow, okay? So to do that, what we do is that we don't just keep track of the Lagrangian itself. We keep track of the Lagrangians with the background turn-on. Okay. So by doing that, then we can actually extract the current along the flow by just taking derivative respect to the gauge fields. So now the flow equation actually has a very nice form. So flow equation now takes this following form. So this is now a flow equation for not just the Lagrangians, but the Lagrangians with the background turn-on. Okay. So this is the flow equation that we want to solve. Okay, and this is a way to define concurrent deformation at an abstract level. So now with this, we can translate it into equations for the partition functions, and which is given by these equations. Okay, and it turns out that this equation looks a bit weird, but it actually has a very simple solutions, and this is what's given by kernel representations. So let me decompose this solutions. So this solution basically says that the partition functions after deformation by lambda is related to the partition function that we start with by integrating against the kernel. Okay, and so here this Z0BA is basically the partition function of the original theories, and B is basically the background gauge fields for that.
You think you need to charge or?
Oh wait. Oh, that's bad. Sorry.
There are some chargers.
Okay, that wouldn't survive. Yeah, give me a second. Yeah. Yeah, sorry. This is so terrible. My mistake. Apologize for this. Oh.
Short the stock.
Yeah. Sorry. Okay.
Because the charge wasn't conserved.
Good. Okay, so now I'm charging the top, I guess. Okay, good. Yeah, so we will survive the top. Okay. Okay. So Okay, good. Yeah, so there's a kernel, and the kernel is a function of the gauge fields B and sorry, a function of B and A, and then we integrate all B. Okay. But notice that, let me make one comment. So even though this B is sitting at the place where a gauge field is supposed to be, this B is actually not a gauge field, okay? And the reason is very simple, because the kernel actually breaks the gauge symmetries. So I'm going to use lowercase letter, little b, to denote a one-form field without a gauge symmetry, and big A to denote a field which actually has a gauge symmetry, okay? So this is what I'm going to do. So this is basically a partition function after deformations. So now let's try to decipher this kernel representation a bit more. So let me first assume that there's no anomaly in the symmetry involved. So that means that the partition function is invariant under shifting the background gauge fields by some gauge transformations. Okay. So if we do that, if the partition function satisfies these properties, then we can actually introduce a Stokerable field, which is a scalar field, to restore the gauge symmetry of little b. So what I do is I just add some little d phi here, and then now there's actually a gauge symmetry now, because if I shift b by some d alpha, I can just compensate it by shifting phi by some alpha. And notice that shifting b by d alpha, it doesn't lift the partition function invariant. So this is actually a gauge symmetry, a valid gauge symmetry of the expression now. Okay.
What is the intuition for the kernel formula? Is there some duality?
What is the intuition?
Yeah, where is it coming? Like, it looks like...
You mean why this is correct?
Yeah,
yeah.
I mean,
So
it looks like if there is a duality, it relates only with coupling.
yeah, okay, so the stupid answer is that it solves the equations, but then there's actually another way to think about it, which I'm coming to much later in the talk. You can think about it as some symmetry operators in a one-dimension higher topological field theories, and then there's actually a very simple interpretation. I'll come into that. I'll come to that. Yeah, just wait a bit. Okay, good. So, so now I actually restore the gauge symmetries. But now, one advantage of restoring this gauge symmetry is that now you can integrate out phi, right? If you integrate out phi, what did you learn? You learn that B is actually flat, okay? So what you're doing now is that you're just summing over partition functions with a flat gauge fields. And then this is actually topological manipulations, because you're just summing over flat gauge fields, okay? And this kind of topological manipulations preserve central charge. So that is consistent with the fact that current deformation preserved conformality. Okay? Good. But now, notice that so far in all my discussions...
Maybe you're about to say, but can you understand this topological manipulation as a gauging?
Yes, yeah. So yeah, let me just say this. So in this case, you can interpret it as doing a topological gauging of the U1.
Of the original, you have two U1s you started with. Right?
Of the two U1.
Of
the
yeah.
two U1, yeah, that's right, yeah. But
in a flat way, yeah.
Yeah, topological gauging just means that I sum over flat connections. So, yeah.
Boundary 2 is like a discrete torsion.
Yeah, there's a discrete torsion. Yeah, there's a discrete torsion here. Yeah, yeah. Good. But I'm going to show you that you can actually get some mileage by knowing that this is a U1 symmetries, and then this allows you to localize these expressions. So let me explain that. So far I have made no informations about that this symmetry is U1. From now on, I'm going to assume that it's actually a U1 symmetry, it's a compact symmetry, and then we can actually get some mileage from this. So for simplicity, I'm going to just consider torus partition functions. Then this things after integrate out phi, I'm just summing over torus partition functions with some symmetry defect inserted, or with some flat holonomy of the background gauge field turn on. Okay. So and then now I'm just my expression just localized to an integral, not a path integral, but just integral over the holonomy. Okay. And then, so this is my expressions. And this just represents the partition functions at lambda equals to 0 with a holonomy turned on. Okay, so this is the formula, the simplified version of this, cartoon version of this. Good. So now notice that for U1 symmetry, then that means that if I shift B by 2 pi times some integers, then the partition function should be invariant, right? Because it's a U1 symmetry, so then the partition function should only depend on the U1 holonomy. So that's why it's independent of shifting big B by 2 pi times integer. Another way to think about it is that if you shift big B by 2 pi times integer, it's like doing large gauge transformations. Okay, good. So now we can actually localize the integral. So what we will do is that I'm going to focus on the case where lambda is 2 pi it's some rational numbers, 2 pi times some rational numbers, where it's given by 2 pi m divided by n, where m and n are coprime. Okay.
So I should think about that phase, the coefficient lambda. Should I think about it as some kind of discrete torsion?
This phase.
Yeah.
Yeah. This is. Hey, wait. Sorry. I think. Oh, sorry. Yeah, that's right. Yeah, this should be interpreted as some discrete torsion. But then when after I localize it, actually has different meaning. I'll come to this. Yeah.
But it's continuous.
It's continuous. So maybe a continuous torsion. But it's a torsion. It's a torsion. Yeah. Okay. Good. So now I'm basically setting lambda to be these things. Okay. So 2 pi m divided by n. So the first things we can do is that we will split the integral of b1, which is supposed to be an integral from minus infinity to infinity, into integral from 0 to 2 pi times some and then a discrete sum of 2 pi times integers. Okay. Then we first perform that sum. If we perform that sum, then that will actually constrains constrains b2 to be 2 pi m times some integer divided by little n. Okay. So this localizes the integral of b2 to a discrete sum. Next, notice that if I focus on those b2, n2, which are 2 pi little n times integers, then that means that my b2 will be 2 pi times integers. Okay, so then I can sum over those first. Then, because my partition function is invariant under those things, then this will further localize b1, and then b1 will now becomes 2 pi times integer divided by little n. So all in all, what have we learned? What we have learned is that by performing this discrete sum first, then we can actually localize the integral into a discrete sum. And the discrete sum basically sums over a z-n gauge field and another z-n gauge field, and then with a term that is given by n1 wedge n2. Okay, so the correct way to interpret this formula is basically saying that if my lambda equals to 2 pi little m divided by n, then my partition function is related to SID theory by just doing the gauging of a zn times zn subgroup of the u1 times u1 symmetry with a discrete torsion. And this is now really a discrete torsion.
I'm just a little confused about the counting. If the two U1s you started with are the same, for example, compact boson, why do you have two ZNs? It would just, in that case, you would have one ZN?
Oh, no, I'll have two ZNs. I'll still have two ZNs. And let me give you an example. Yeah, that maybe will be helpful.
Write down this current deformation. You have to start with J.
You need a
You have two U1.
It's J1 wedge J2.
In the case of compact boson, there are also two U1.
That's true, okay.
Yeah. Good. So now let's talk about this. So what in summary, basically saying that non-anomalous current deformations with a rational lambda can be thought of as gauging a zn times zn subgroup with discrete torsion. But now let's just take n to be 1, okay? If we take n to be 1, we're basically gauging nothing, right? We're gauging z1, which is nothing. So that means that the theory after deformation is actually identical to a SID theory. So what we have learned is that if we increase lambda from 0 to 2 pi, we're actually going back to the same theories. So that means that the deformations that we're talking about is actually tracing out a closed cycle on the conformal manifold. Okay? And let me discuss an example. And the example is basically just given by the B field of a C equals to 2 non-CFT. So now we have two compact bosons. And then we have two winding currents, which are basically the currents that measure the winding charge of the two compact bosons. And this two currents has no mixed anomaly. Okay, so this satisfies my conditions. And now if I do a deformation with these two currents, it turns out that it's just basically turning on a B field. And the B field that we turn on has a coefficient given by lambda. And it turns out that we know that B field is periodic. And it's just because the term that the B field multiplied is an integer. So that's why we learned that lambda is periodic, and this is consistent with the statement that the non-anomalous current deformation is actually tracing out the closed circle on the conformal manifold. Okay, so this is the case where there's no anomaly, but now let's ask what happens if there's an anomaly, okay? So I'm going to assume that there's a mixed anomaly between the two symmetries, which is similar to a compact boson case. So in this case, there are two U1 symmetries, but now there's a mixed anomaly between them. And a mixed anomaly basically tells us that now the partition function is not invariant under the gauge symmetry, but actually transformed by a phase. Okay? So now we can again restore the gauge symmetry by introducing the Stocker field. And by doing so, now we need to add additional terms, which also compensate the gauge transformations of the partition functions. Okay, so this is how we will restore the gauge symmetries. And now we can do the same things. We can just integrate out phi, and then ask what happens to the gauge fields. But notice that when you integrate out phi, now there's actually a problem at some special points. So at generic point, we basically just set B1 and B2 to be flat. So this is a topological manipulations. But at a very special point, in particular, when lambda equals to 2 pi, then it turns out that B1 is actually not constrained. Okay, so I'm going to come back to the physical meaning why this is not constrained later. And also notice that lambda equals to minus infinity and positive infinity is also not constrained. But otherwise it's clear that away from those points, the kernel representation is just implementing a topological manipulations. So the central charge is preserved. Good. So now let's do the same game as before. We again talk about rational points. So I'm going to take, but before talking about rational points, let me make a comments about the partition functions of the SID theories. What happens to that if we shift holonomy by 2 pi times integer? So before, when there's no anomaly, if we shift the holonomy by 2 pi times integer, the partition function is invariant. But now because there's a holonomy, then the partition function may not be invariant. It is because if we shift b by 2 pi times integer, it's actually doing a large gauge transformations. And we know that the partition function is not invariant under the gauge transformations. So in particular, it will not be invariant under large gauge transformations. So the way the partition function will transform is like it will generate an extra phase that is proportional to k2, which is the parameter that shifts b2 by. And then it will generate a phase that is proportional to b1 wedge k2, okay? So now we need to take this into account when we do the discrete sum. Good, so now let's do the same thing as before. Let's consider rational points, 2 pi times rational numbers point. And then in this case, we can first sum over b1. If you sum over b1, notice that the partition function is actually invariant under shifting b1. So that means that if I sum over b1, I'm basically setting b2 to be 2 pi little m times some integer divided by little n. Next, I'm going to sum over b2, which are n times integers. Sorry, there's no 2 pi. N times integers, so that b2 is 2 pi times integers. So, but when I do that, I need to take into account that the partition function is actually not exactly invariant under shifting b2 by some 2 pi times integers. So if I take that into account, what I learned is that b1 is now localized to be 2 pi times the integer divided by n minus m. Okay, so there's an important minus m here now, which is different from the non-anomalous case. Okay, so when the dust settles, this is the final formula. The formula basically just says that we are not doing not an integral but a discrete sum, and this discrete sum is basically just amounts to summing over a z n minus m gauge fields and a z n gauge fields, and then with a term given by this. But what's the way to interpret this? The way to interpret this turns out that it amounts to gauging a z n minus 1 m times z n subgroup of the u1 times u1 symmetry. And there are two comments to make. One comment is that even though u1 times u1 symmetry has an anomaly, this subgroup is actually anomaly free. So we can actually gauge that, okay? So this is a valid thing to do. Second thing is that before we interpret this as doing some discrete torsion, but in fact, there's actually, here the correct interpretation of this is that this is not doing a discrete torsion. The term added here is just to introduce to trivialize the anomalies, okay? So what I'm doing is I'm doing a vanilla gauging of a z n minus n times z n subgroup. And in fact, this two symmetry there's no way to turn on a discrete torsion between these two subgroups because the n minus m and n are actually co-prime, so there's actually no discrete torsion to turn on. Okay, so this is a bit different from the non-anomalous case. There's no discrete torsion, and the group we are gauging are a little bit different.
If you turn here, you assume you have 1 unit of anomaly.
I'm assuming there's one unit of anomaly.
For higher units, you change the coefficient in front of n.
That's right, correct, yeah, that's correct. Good, so now let me summarize. So when there's an anomaly, then the current deformation at rational points just amounts to gauging, doing a vanilla gauging of a z n minus m and a z n subgroup without a discrete torsion, okay? But what can we learn? So one thing we can learn is that we can actually show that the special point that I talked about where the flatness condition fell, namely the lambda equals to plus infinity and minus infinity and 2 point points are actually infinitely same points. So that's why they actually that's why they actually failed. The flatness condition failed. So how to show this? So the way to show this is that let's say we're interested at lambda equals to positive infinity, then we can approach that by a discrete sequence. Okay, what we do is that we set n to be 1 and n, then lambda will be 2 pi times n. And then I just make n bigger and bigger, and then eventually I'll approach infinity. But if I consider this special case, then what I'm doing is that I'm basically just gauging a z1 minus n times z1 subgroup, right? But z1 subgroup means nothing, so I'm just gauging a z1 minus m subgroup. But when I gauge a z1 minus m subgroup, notice that I'll introduce some twisted sectors. Okay, so the twisted sectors are basically operators that are living at the endpoint of the group of the symmetry defects that I'm gauging. But notice that when I take m to be bigger and bigger, the twists that appear in the twisted sector are actually finer and finer. So, and because the dimension of the twisted sector operators is actually a smooth function of the twist, but now the twist has become finer and finer, so that just means that there exists an operator whose dimension is actually approaching 0. Well, approaching the lowest, approaching the dimension of the identity operators as m increases. But then this basically is what Hiroshi and Ifan proved in their papers, that if there's an operator whose scalar dimension actually going to 0 in the limit, then this is basically an infinite distance point on conformal manifold. Okay, so here we have shown that lambda at positive infinity and minus infinity, they're at infinite distance. Okay, but what about 2 pi? So 2 pi, we can approach that by taking m to be n minus 1. And if I take m to be n minus 1, then this is basically 2 pi minus 2 pi over n, right? Then I just take n to be larger and larger, then I'm actually closer and closer to 2 pi. So in that case, if I do, I can basically play the same game. So in this particular case, if I set m to be n minus 1, then I'm basically just gauging a z1 subgroup times a zn subgroup. z1 again is not doing anything, I'm just gauging a zn subgroup. By using the same argument as before, if I take n to be bigger and bigger, I'm actually introducing more and more twisted sector operators. And eventually, when I take n to be infinity, then there's an operator whose dimension actually vanishes in the limit. So again, using the result by Hiroshi and Ifan, one can show that lambda equals to 2 pi is actually at the infinite distance of the conformal manifold. Okay, so this is what we have learned. So okay, so let me now do an example. So let's ask what happens if we do a current deformations on a C equals to 1 compact boson CFT. So in this theories, there are 2 currents one can use. One is the currents that amounts to shifting phi by constants, and the other is the currents about that is measuring the winding charge of the phi. Okay, and so these 2 currents has a mixed anomaly. So this fitting my assumptions. So in this case, if you really do the current deformations correctly, you'll find that the radius is actually changing by nonlinear functions of lambda. Because when we do deformations, the currents is actually changing with respect to a function of lambda. Okay, so here we see that this nonlinear functions indeed blows up when lambda equals to 2 pi. So lambda equals to 2 pi, the radius is infinite. So it's an infinite distant point on conformal manifold. When lambda equals to plus or minus infinity, the radius is 0. So it's again an infinite distant point on conformal manifold.
Is lambda 0 the point you started with?
No, lambda equals 0 is the point I started with.
Yeah, so
lambda equals 0.
How can I get to plus infinity? I have to hit 2 pi first.
Yeah, so you actually bounce back. yeah. Yeah.
Shouldn't I expect like a conformal metric to emerge at this near this point on the conformal manifold?
What do you mean by conformal metric?
The metric to look like an ADS type metric.
ADS type
at
metric.
infinite distance.
In the target space you're talking about. So you're talking about the metric on the conformal manifold, right? Mm-hmm. Yeah. Also, in this case, because there's only radius, so you will just see
should get something like dr of r squared.
Yeah, you get a metric like that. Yeah, that's right.
Could you see that? Could you see that more explicitly? Could you show that that's generically the case?
So in this example, we can actually compute the metric directly. Okay. Yeah, but I didn't show it using the current deformations. In principle, one should be able to compute the metric from the current deformations.
Because that was one of the criteria, whether it's like when you have an actual decoupling at an infinite point, that you should get some conformal emergent metric where you can have like a stupid decoupling point where you where there's nothing to decouple. An infinite distant point where things aren't decoupling, you shouldn't get a conformal metric.
Oh, I see. Yeah, I didn't.
Metric for the JJ bar marginalized, like some two-point function.
Yeah,
The
yeah.
currents, and you can compute that.
That can be computed, yeah. And that as Ibu said, it's I think it's some
Okay, thank you.
dr over.
Sorry, what is the subscript little a? Do you have a single boson or just two?
Little a, where's the?
The line.
Oh, sorry, I have a single boson. A should be 0. There's no a. There's no a. Sorry.
So let's see. Why did you put an r squared in the definition of J1?
R squared. Oh, because I want to always normalize my currents to be U1 currents. So if I integrate this current, I'll get the integer charge.
I'm a little puzzled because if you hadn't put it there, it looks like, well, maybe, I don't know what your conventions are exactly, but is J1 wedge to J2 T-duality invariant?
G1 wedge J2.
T-duality invariant?
I think it's
It looks pretty close to T-duality.
I think it's T-duality invariant.
Okay, then I'm confused why your Lagrangian isn't. If you're adding a T-duality invariant deformation, why isn't the result T-duality invariant?
Yeah. The reason is when I do the couplings, I break the. So when I do the deformation, I need to couple the Lagrangians to background gauge fields, and the coupling breaks the T-duality. Yeah. Because I really not.
Would it be possible to do this procedure in a T-duality invariant way all the way around?
I think I think that's actually possible. Yeah. I only consider the one that breaks the T-duality invariance. Yeah, that's possible. Okay, good. So let me now make a.
Let me put it this way: the original theory has a T-duality invariance, and the final theory has a T-duality invariance.
Oh, then you say we are not flowing at all.
How are they related? It looks very complicated. The formula for the new radius looks complicated.
You mean why we have this formula?
Well, L0 has a T-duality invariance.
Yeah.
L sub lambda has a T-duality invariance.
Sorry. This is only T-duality invariance if you have at a particular radius, right? Are you talking about that radius?
The family of theories parameterized by R,
Yes.
L0, has a T-duality invariance.
Yeah, that's right.
Same thing is true for the family of theories parameterized by R.
Mm-hmm. Yeah.
It's a redundant parameterization because it only depends on this particular function of R length. Nevertheless, that family of theories has a T-duality invariance. Odd. Seems like you should have been able to relate those two T-duality invariances of the two families of it's the same family of theories.
Yeah, I think here is because I choose a coupling that breaks the T-duality invariance, but I think there's a way to preserve T-duality invariance. Yeah, we can talk about that later.
I have a question about this one.
Okay.
Yeah, so here, in this first bullet point, what do you mean by twist? Is twist the H or the scaling?
Oh, sorry. When I say twist, I mean it's the parameters that appears in the symmetry operators that label the twisted sectors. The parameter that label the twisted sector. So the symmetry operator that is given by 2 pi divided by little n times integral. Yeah, Greg, let's talk about this.
Let me put the question a different way.
Yes.
Take L0. You have L0, it depends on R.
Yes.
Let's take L0 prime to be same Lagrangian with R goes to 1 over R.
Yeah,
Those are exactly the same theories.
that's right. Yeah.
Therefore, if I do a perturbation on L0 with R, there's a corresponding perturbation on L0 prime with 1 over R.
That's right. That's right.
They should flow to equivalent theories because you're just writing the same theory in 2 different ways.
Oh, that's right.
Okay. And so I'm just saying that that symmetry is not obvious from your formulas. And I was wondering if there's a way to present it in a slightly your transformation in a different way that makes that symmetry obvious.
Yeah, there's a way. So let me make a comment related to that. So here, this flow, when I derive the flow, actually I need to specify how the symmetry are coupled to background gauge fields. And here I picked a way the coupling actually doesn't preserve T-duality. So that's why the final results seems to be, if I change R to be 1 over R, I'm swapping these two currents. And then because my coupling actually doesn't.
I understand your procedure breaks symmetry, but then you're starting with an equivalent theory. There has to be a different coupling to a different gauge field that gives you an equivalent theory at the end.
Oh yeah, certainly, yeah. That I agree, yeah. That I agree, yeah, for sure. Yeah. Okay, good. So let me continue. So let me now make a comment about enhanced symmetries. So often the case on conformal manifolds, there are some special points with enhanced symmetries. And a simple example is just given by C equals to 1 compact boson CFT. And we know that there's actually at a self-field radius. So away from self-field radius, usually we say that there's a U1 times U1 symmetries. One corresponds to the shift symmetry, and the other corresponds to the winding symmetries. But at the self-field radius, the symmetry actually enhances to SU2 times SU2 divided by Z2. Okay, and usually we would say that the symmetry is enhanced there, and the symmetry is broken down to U1 times U1 because the current deformation breaks the symmetry down. But now, by knowing the fact that the points living on a current deformations conformal manifolds are related to SID theory by doing some discrete gaugings, then if I take a radius to be m divided by little n, where m and n are coprime integers, then we know that these 2 points are actually related by gauging a Zn subgroup and a Zm subgroup of the U1 times U1 symmetries. So that means that the symmetry that we thought are broken, they actually got recombined into non-invertible symmetries at this point. And these non-invertible symmetries are parameterized by this coset. So how to think about this non-invertible symmetry? There's actually a very simple way to think about it. Is that let's first imagine that we have a theory at radius m divided by little n, okay? Then we can first imagine that there's a little interval, and within the interval is r equals to 1. And there's actually a topological interface between these two theories that are related by gauging, okay? And then in the middle of the interval, I can now insert a symmetry defect at r equals to 1. And that symmetry defect is parameterized by this SU2 times SU2 mod Z2 symmetries. Then if I take these things to be very, very thin, then this will define for me a symmetry operators. And these symmetry operators are labeled by the coset, by this double coset, okay? And it turns out that these symmetry operators, if you fuse them, you don't just get one symmetry operator out. So it's not like a unitary symmetries. You actually get multiple symmetry operators coming out. And the things that comes out is basically G times H, and then with Zn symmetry, all possible Zn symmetry inserted, and all possible Zm symmetry inserted. Okay, so you basically get a non-invertible symmetry at this point. So the takeaway is that at least on the conformal manifold generated by current deformations, the enhanced invertible symmetry actually turns into non-invertible symmetries on the conformal manifold. So this is a takeaway. I think I only have 2.5 minutes, so I'll be very brief about the SymTFT pictures. So first of all, for people who are not familiar with SymTFTs, this is basically short for symmetry topological field theory. So this is a framework that characterizes global symmetries using topological field theories in one dimension higher. And what it does is that it allows us to separate the universal kinematics associated to a global symmetry from dynamics of the theory by decomposing the theory into a sandwich. So the rough idea is basically that if we have a theory like this, we can divide it into 2 parts, where in the middle is a topological field theory that characterizes the symmetries, and on the left contains all the dynamical degrees of freedom. So in particular, if we start with CFT, then this will be a gapless boundary conditions. And on the other hand, for the other one, this will be a topological boundary condition, so it's a gap boundary conditions. And then if we modify this topological boundary condition. Sorry, let me say one more thing. So because this is a topological boundary conditions, and the SymTFT is also topological, so then that means that the width of this doesn't matter. You can actually squeeze it. And then this allows you to reduce a sandwich which has a thickness to something that has no thickness. So that allows you to reduce D plus one dimensional systems to D dimensional systems. Okay? And one important thing about SymTFT is that if you give me a topological boundary conditions, I can change it. If I change it to the other topological boundary conditions, then it amounts to implementing the topological manipulations. So in particular, you can think about discrete overfolding or gauging by changing the topological boundary conditions of the SymTFTs. So now, since I told you that concurrent deformations are basically doing some topological manipulations, then this means that it must have some nice interpretations in the sim TFTs. So in particular, the symmetry TFT that I'm going to use involve U1 times U1 symmetries. And the sim TFT is given by 2 copies of BF theories, where one of the B is R gauge fields and the other A is actually U1 gauge fields. Okay? And if you look at this, the equation of motion of B or A constrains each other to be flat. And then furthermore, if you sum over the flux sector of big A, that tells you that B has to be integer quantized. And now you can actually recover the symmetry, or you can talk about what are the symmetries in these theories by looking at some particular topological boundary conditions. So in particular, there's always a canonical boundary conditions, which is a tertiary boundary conditions that set big A to be 0. And to set big A to be 0, you basically add up boundary terms like this, and then the equation of motion of little b automatically will impose that A is 0. And the equation of motion of A gets trivialized, so there's no interesting equation of motion of A. And now on these boundaries, what happens is that you can talk about an operator that are made of B. You just integrate B over some surfaces, and this operator will be integerally quantized because of the equation of motion of A. And then this integerally quantized operators can be interpreted as a symmetry charge of the U1 symmetries. So one important takeaway is that this little b should be sort of as some currents for there's another currents for the U1 symmetries. So now we can discuss how to think about current deformations. So the way to think about current deformation is that basically in this U1 times U1 sim TFTs, there are actually a topological surface operators we can talk about, which is given by B1 wedge B2. And then you're allowed to add some coefficient in the front. And it turns out that this coefficient has some 2-pi periodicity because B1 wedge B2 is integral. So this is actually generating U1 symmetries. And when we have some topological boundary conditions that we start with, then we can always insert this topological surface defects and then push it to the boundaries. Then this will generate a new gap boundary conditions. And that new gap boundary conditions will correspond to doing some topological manipulations. But now, these operators, if you think about this, because I told you that on the derivative boundary conditions, B1 and B2 are basically currents. But these are basically just doing the current operators, right? So if I push these operators to the boundaries, I can integrate a little b, then I get this kernel. So this is the familiar kernel that I wrote down before. So what's the lesson? The lesson is basically, if I push this symmetry operators to the boundaries, I basically get the boundary conditions that implement the current deformations. And the fact that the current deformation is tracing out a closed cycle with lambda, well, when there's no anomaly, it's just because this is a U1 symmetry.
I would say that if you push this on the other boundary,
yes.
The one where you put like these 3 boundary conditions, then B is the current in the CFT, no?
B is
the small b is the current.
Yeah, B
on
is
the other
B,
side, though.
Oh, you say you want to push it to the other side?
Yeah. Then if you do it like in Chen-Simon's theory, for example, that's how you get the currents in the.
One should probably, maybe let's talk about this. I should probably conclude. Okay.
Well, it's a 0 from symmetry in the sim TFT. I guess you would call it a -1 from symmetry.
Exactly. Yeah, and then changing doing concurrent deformation is like generating a -1 from symmetry. Yeah. So let me just conclude. I'm not going to say too much about it. Let me just conclude saying, okay, so in the talk we discussed concurrent deformations, and then and one important lesson is that even though concurrent deformation seems to be a smooth process, its various global properties actually change very erratically along the deformations. And we show that rationally dense set of points are related to a SID theory by discrete gauging, and this allows us to relate topology with the anomalies of occurrence. And in particular, one important takeaway is that enhancing invertible symmetry actually get reorganized into non-invertible symmetries after concurrent deformations. And then we can also interpret concurrent deformations as some 0 from symmetry in the sim TFTs. So let me just end with this future direction slides. Thanks, everyone. Yeah.